Okay, today we're going to go over transforming sine waves. Yesterday we talked about it a little. We're going to show you with changing certain numbers what it can do to a sine wave. Now, the letters they're using here, they have an A, a B, and a C variable. Not what we're using. And in fact, we're not actually going to talk about the B. In our case, B will always be 1. I'll show you exactly what letters they're referring to and then what we use them as. They're talking that f at x is equal to, A is the term in front of sine. Now in theirs, B is the coefficient in front of the x. For us, that coefficient is always going to be 1. And then they're talking about plus C. Okay? Now what we're technically dealing with is, again, we're going to have the same A as them. Sine. Now B will be 1. So I'm going to write 1 in there. X. And then we're going to use minus H just because we use that letter when talking about parabolas. And it does technically the same thing. Plus K. Okay? Now in this little program we have here, they don't actually have a K. So we can't do what with the sine wave. Anyone know? We can't move it up and down. It's just going to stay. The equation of the axis is always going to be on the x-axis here. Okay? So, what we're going to do, first of all, is we're going to talk about C. When our number C is 0, we're at our normal spot in a sine wave. Okay? When we move the number to 1, you'll see it starts to shift. Which direction did it shift? When I went in a positive direction.
Yeah.
Do you see how it's moving left? So I keep going, it keeps going left. And these are positive numbers. Okay? As I start going the other way.
We're not really making differences. It's forever, right?
Yeah, in a negative direction. Okay? It's going to the right. Now they're using numbers like, or they're using units of 1, 2, 3, and their x-axis is actually measured off of, looks like 1, 2, 3. But what we're going to be doing is we're going to be using degrees. So most of our movements will be something like 30 degrees, 45 degrees, 60 degrees, 90, 180. We'll do increments of 3 or 45, something like that. Okay? Just because those are important terms when it comes to trigonometry. 30, 45, 60, 90. Okay? So, you guys saw that moving left and right?
Make it 0, please.
Yes. There you go. Okay? There's our normal one. So that's when our C is a positive number, it goes to the left. And when it is a negative number, we shift to the right. Now, K would move it up and down. We don't have that function in this program, so we're kind of going to skip it. It's the same idea, just the whole wave goes up and down. A changes things quite a bit. Okay? Our A here in our normal function, I'm going to show you what I mean by our normal function here. Technically, we're dealing with when all things are even. F at x is 1 sine x minus 0, can I fit it? Plus 0. Okay? So, our h and our k in this function here are both 0, but our a is technically the number 1. What is our amplitude in our normal sine x? 1. Our amplitude is 1. We're going to try to zoom in a little here. Alright, so as we zoom in, let's go a little more here. There we go, that's a little better. Okay, so as we zoom into this, it's a little much. That's okay. Our amplitude, if you guys notice, goes from the equation of the axis up to a peak, and from the equation of the axis down to a trough. And in this case, how far are both of those? 1. What is our A value? 1. Our A value is actually always going to be what our amplitude of the wave is. So as I change this, and I'm going to need to zoom out a little again, so bear with me. Change a little, and I'll erase those.
What A stands for?
It deals with the vertical stretch, is what A stands for. Okay? So, in this case, when I change our A from 1 to the number 2, you're going to notice this is going to become more stretched. Now, what's important is I'm going to clarify these points before we get into it, actually. Our zeros are still going to be 0. So we're going to cross our equation of the axis at the exact same point. What I want you guys to think of it as is your peaks and your troughs, or essentially your amplitude, get multiplied by that term. So my highest point here is 1. When I change it to 2, the highest point will then be 2, and the lowest point will then be 2. But these key points, and we're multiplying the y values of the points. The x values, nothing changes with them. When you multiply, for instance, our highest point was 1. When I multiply that by 2, we get our number 2. This point here was -1. When the a value changes to 2, so we multiply by 2, the lowest point becomes -2. What about this point here? What's the y value of that?
0.
So what is 0 times 2?
0.
So what does that mean? Is that point going to move?
No.
That point should stay the same. So let's take a look at it. We move this up to 2, and it exactly fits what we predicted it was going to fit. The zeros stay the exact same, and our peaks and our trough get moved by a new amplitude of 2. So obviously, if I click it to 3, what's going to happen?
Okay.
We go up to 3 and 4. Now, let's go back to 1. If a was 0, anyone know what would happen?
Straight line. Yes, straight line.
Flat line, because 0 times anything is going to be 0. Okay? So we're going to put it down to 0. You notice we have a flat line right now. We're not really going to work with those sine waves at all.
So 0 wouldn't be a sine wave, or would it still be?
Or no, because it won't be a sine wave. The sine x times 0 will just be 0. Okay, so all of our y values will be 0 in this case. Now, this is the important part. I want you guys to recognize something. When I go into the negative, it's actually a flipped version of the original one. Okay? So, remember, our -1 down here, and we have a -1 down here. I'm going to move that. Also the -2 and +2. I think this is being measured in radians right now. And remember, we work with degrees. We wouldn't be using units of 1, 2, 3. I just wanted you guys to get used to the idea of this program. So, when I change this to -2, our peak and our trough both stretch farther in the negative direction. So the red points represent negative a values, and our purple points represent positive a values. So what has happened is this has been flipped on the x-axis. It's as if we drew a line directly through the middle of this and flipped it upside down. Okay? So when that happens, we get something like this. So when a is +2, I'm just going to use the example of -2. It would still be the same amplitude, but this point is going to end up down there, and this point is going to end up here, okay? When we change it to a negative term. So when I change it to a negative term, instead of -2, you see that the points have now flipped from their original spot. The wave itself, nothing else has really happened to it. It's just stretched and been flipped. So when a is negative, it flips the wave, and depending on what the a value is, it changes the amplitude of the wave. Okay, so we have this question here. They've given us a sine wave. Our a value, you know, we'll write out again what each of these we wanted them to stand for. So remember, this is technically f at x is equal to a sine x minus some value plus another value. And those letters that we use are A, H, and K. Okay. So what is our K value in this one?
1.
Oh, is it 1? What's our H value?
-270.
-270. And our A value? -4. Good. So we have our A, H, and K. Now, there was a shortcut I told you about A, the absolute value of it. What is the absolute value of A also give you? Amplitude, right? K also gives us something, okay? There's another equation up here we have. The equation of the axis can be put in, or we can tell what it is by looking at K. So normally, I'm going to draw what our normal function is, okay? F at x is equal to sine x. That's how they normally describe this. And what I'm going to do is I'm going to show you what the values of H, A, and K are in this one right here. In this case, they don't include these numbers because 1 times sine x is just sine x. x minus 0 is still x, and plus 0 is still sine x. So technically, I have an h value of 0. I haven't moved it anywhere from the original. A k value of 0. So the equation of the axis is on what? Y equals, oh no, 0. And our a value is 1, so our amplitude is what? 1. So our original equation, sine x, we know how to plot it. 0 and 0, 1 and 90, 0, 180, negative 1 to 70. And we continue this pattern. So this goes down, up, down, down.
That's the normal pattern.
This is the normal pattern. We just followed.
That's cool.
Once we had the first major 5 points, we just followed them. Okay, so this is our original sine graph. Now what we're going to talk about is our changes to it. I like to start with stretching graphs or compressing them first, but it's up to you guys how you want to do this. Our first one is negative 4. So first of all, because a is a negative, what did I say was going to happen?
Flip.
All of the major points are going to flip. So this peak will now become a trough. This trough will now become a peak. Okay? So we'll outline that one, I suppose, in red. And what I'm doing right now is I'm going to do this one step at a time. I should really make this deeper down here. It's okay.
Yeah, you can't do that on tests, Nate. Oh, it's cold.
There you go. And I'm just going to erase those other points for now. We know what they are.
I'm so confused. What's the point?
I needed more room. I just needed more room. Okay, so what I'm going to do now is I'm going to do f at x is equal to negative sine x. So I'm doing one step at a time. Because we had negative 4, I'm dealing with the negative part. So all I really have to do here, is he drawn properly? Yeah. Is our zeros have the same value, but our peaks and our troughs have moved just a little. Okay, they flipped exactly upside down. I don't think I put that one exactly. Because that is what A will do. Whoops, sorry. Kind of looks like a DNA strand there. Okay, so when A is negative, it's what our red wave looks like. It's the opposite of our original one. We flipped it. I know I didn't do a great job filling in this.
You did a perfect job.
Thank you. Now, the next thing we're going to talk about is, we'll change this to purple, I guess. F at x is equal to negative 4. So our A value is now negative 4 sine x. I still haven't done anything else. Now, our red one is set up properly. Our peaks and troughs are on the right sides of the equation of the axis. The only difference is, instead of having amplitude of 1, what's our new amplitude going to be?
4.
4. So,
-4.
you know what? It doesn't even fit on this graph, so let's change that number to 3.
You're cold, sir. You just changed my whole answer, sir.
Sorry.
You're cold, sir.
So we're going to say
Shut up.
negative 3 instead.
Or next.
Am I missing the S?
Put 2.
Okay.
2 better.
So we have 3. So what that means now, instead of our units or amplitude being 1, I just pull the peak up to 3. My 0, remember, is the exact same. Now this used to be a 1. So all I did is I took that 1 and multiplied by 3, and I knew to go to number 3. Okay, now if I've actually transformed this graph first, this little trick won't really work. That's why I do this one first before I move it up and down or left to right. When I move it up and down and I try that trick, it doesn't quite work. Okay, it's really going to change this. This only works when the equation of the axis is directly on 0. Okay, so I also take my trough, I stretch that down to 3. So this is the same type of wave. The only difference is it has a much larger amplitude to it. So when we follow this, this will not be as well done.
Sir, if you take rocks off the drop, is it perfect?
It needs to be set up like a wave. Oh, jeez. That one wasn't
You're
good.
cold, sir.
Okay. So there's our purple version. That's when our A value is negative 3. Now from there, the next thing we talked about is a movement of 270 degrees. So the next one I'm going to do, f at x is equal to negative 3 sine x minus 270. Now, if we're subtracting, which direction do we go?
Right.
We go to the right. We go in a positive direction. So I'm going to take these major points. This one here.
Okay. That's cool.
Oops.
You're not ready.
That major point there. This major point down here. We're going to move each of them 270 degrees to the right. Okay? So right now, a way to do this is to actually look at the x values and subtract if you can't do it by just looking at it. So this x value here is negative 450. Okay, I'm talking about this point right here. The x value is at negative 450. I got to go in a positive direction 270, so if I add 270 to it, anyone know what I'm going to get?
360.
Right? 270. 540.
Let's work on it. Okay. So
90.
here,
180.
here's a way you can do it if you're not sure how.
Shit, it's 180.
450
Oh, it's
plus,
180.
yes, there you go.
Negative
270.
180.
Good. Negative 180. Okay? So I take this high point and I move it over to negative 180, which is normally right here. Okay? Now, what I really want you guys to notice is a trick to this is 270. Since this graph is in 90-degree increments, think of it, 270 would be technically 90 times 3. So it's like I moved it 3 major points. Here was one of them, so I moved over 1. Here's another one, 2, and then here's the third major point, 3. So I moved it over 3 major points. Okay, and now I just do that with every single point along this. I move them all 3 major points to the right. So that was this point here. This guy goes over 1, 2, 3. Take this point here, we go over 1, 2, 3. And then once I have a line of it, I have a good idea of how to draw the rest of this thing.
So is it alright if your thing looks like this, your paper?
Yeah.
And then you just point to the last step?
Yes, if you want to. So I'm just going to continue it from what we have. So we have an idea here.
That's how I do it. It's hard to understand.
But you kind of have to, unless you do it in your head. That's hard.
So we have the blue. I know it's a little confusing. Technically, it goes up again to here. Okay. Now, I notice you guys are a little confused with what we got here. So what I'm going to do is I'm going to clear this off and show us a new one. And the last thing we still have to deal with,
Move it up one.
1. This is a lot simpler. We just take each of these and move them up 1. Now, I know that 4 is technically not on this. So this high point of 3 has to go up to 4. This point that's at a 0 jumps up to a 1. This point at 3. Oh, sorry, we're on the blue guy here.
Oscar cold, man.
So this goes up to 1. This goes up to negative 2.
Using his phone while he was like sleeping.
1.
Who did?
4.
4. Good.
1.
Yep. And 1. So the idea of this here,
That's a lot of steps.
we take each of the major points and we just shift it up 1 unit.
So this is like the hardest thing we can do, right?
This would be the all of the steps together in 1.
Yeah.
So our green one is essentially the left. I know it looks very confusing here. I won't give you one that's so in-depth. But this would be the most complex thing you can do, where it's a flipped graph, it's been stretched by 3, moved to the right 270, and shifted up 1. That would be all 4 steps put together. Okay, so here's another version of it. Last time I'm going to mention this. So this program here measures in radians. So what I want you guys to realize, first of all, the A value in front of this is technically the number 1. So when I write 1 in, it hasn't changed the wave. It's the exact same thing. My X value, if I subtract by 0, doesn't change anything. And if I add 0 at the end, still doesn't change anything. It's the exact same wave, which is essentially our original wave. Now we said that our A value in this one was going to be a negative number, so I'm going to do negative sine. Okay? Then we're going to turn it on. That's what negative sine looks like. It's a flipped version of it. Next step we did was an amplitude of 3, or an A value of 3. So it's going to look like the red one, but be stretched by 3 units.
Okay.
So now it's been stretched up 3 units. The next one we did,
So here they almost stretched it up by
Theirs is 3.
It's 3 from the 0.
Yeah.
I said it's supposed to be 3 from the point.
We're going to move that point in a second.
Oh, okay.
Now, I'm not going to change 270 because these units aren't measured in 270. Remember I said that a 270 movement on our graph, because our graph was measured in 90 degrees, looked like 3 movements. I'm going to move it by 3, okay? Just because this x-axis isn't measured in degrees. So I'm going to move it to the right 3. And then we'll turn it on. So the purple graph, okay, has been moved to the right 3 units. So it's a little off of the green one, if you guys notice, okay? And then finally, the last one here, we moved it up by 1. Oops. So -3 plus 1. And he's going to move, it's going to go from the purple one up 1 unit. So what that actually means is this is our final graph here. That's what's happened. It's been shifted up. Our equation of the axis is now at 1. Our amplitude is now 3. And we've moved, instead of 273 units to the right, and it's been flipped from the original one. And if you turn all of these back on, you can see those movements. So that's moving it down 1. This would be moving it down 1 and back 3 units. This one would be just the original, just flipped upside down, and this is our very original one. So from the original one, it's quite a different looking graph from what we have.
It's the light blue. It's the original.
Light blue I haven't done anything with.
What's the first one?
So this program is called graph.tk. You need Google Chrome.
Yes.
It's a free account.
Yes.
Download
Yes.
it. It helps very much.
Close.